The other thing that affects fluidity more than permeability is cholesterol. So this is the only example of a sort of phospholipid membrane, phospholipid bilayer membrane that I could find with cholesterol in it, and used as an example. So this is our cholesterol. So it's the same rules apply. It's just a vesicle. It's just a vesicle. But equally, so cholesterol is one of those structures, and I've sort of drawn it like this multiple times. Basically, it's just loads of C and CH bonds, so it's really, really non-polar. And because of this, it's very good at forming non-polar groups. It's very good at forming bonds with other non-polar groups, like the lipid tails of the phospholipid membrane. So it forms lots of bonds with the things around it. So effectively, actually, and it doesn't make full sense because it's so non-polar. It's very good at forming these bonds, and these phospholipids actually become worse at sort of swapping with one another. So cholesterol decreases the fluidity of the membrane. The problem we have with OCR is they sort of change what reasoning they have, and the textbook actually says it does both. So if you see something saying that it increases the fluidity of a membrane, you need to check how old the mark scheme is. At the moment, from what I can see, it's saying it decreases the fluidity of the membrane for this reasoning. The way it can increase the fluidity of the membrane is because it's sort of less well structured or less similarly structured. It sort of causes these phospholipids to kink with one another, and therefore the bonds they form between each other aren't as strong as they otherwise would be, and therefore you have increased availability for these things to swap. In reality, it's concentration dependent. So if you've got loads of cholesterol, it will change the fluidity in a different way to if you have very little. But at the moment, let's stick with decreased fluidity.